In this problem, we are given this uniform thin square plate. Its mass is m, and it's also a solid plate. And this dimension is L because this is a square, therefore this dimension is L as well. And we need to determine the mass moment of inertia of this plate about this y-axis, which crosses its gravitational center G. So to derive this formula, we know that as a general equation, mass moment of inertia about any axis equals to the integration of r squared dm integrated over the entire body, and this r here is the perpendicular distance to this axis that we're calculating the moment of inertia about. So this right here is the differential element with the very, very small mass of dm. So in this case, we're going to first choose our integration element. We're going to, instead of choosing a small element like this with dx dy, we are actually going to choose a differential element that is a little strip. The reason why we can choose this strip is because any point on this strip, so if this is our x-axis, then this little width right here is dx. And the reason why we can choose this strip is because any point on this strip have the same distance to y, and that distance is actually x. So for that reason, we can choose this strip as our differential element. Now, because this is a uniform thin plate, therefore dm equals to rho, the density, times dv times the volume. And if the thickness of the plate is t, so dv equals to t times dA, the area. And in this case, we know that this length is L, therefore this can be further written as rho times t times L dx. So again, these together is your dA, that's the differential area. T times dA is your dV, and rho times dV is your dm. So with that preparation done, the mass moment of inertia about the y-axis equals to simply x squared times dm, which is rho t L dx. Integrated now for the entire body, which is when x equals to negative half an L, because here is when x equals to 0, this is where y-axis is, to from the left side to the right end is x equals to positive half an L. So integrated from negative half an L to positive half an L. So rho t and L, they are all constants. So this becomes integrating from negative half an L to positive half an L, x squared dx, which equals to rho times t times L, 1/3 x to the third power evaluated from negative half an L to positive half an L. This equals to rho t L times 1/3 half an L to the third power minus negative half an L to the third power. So this is 1/8 of an L to the third power minus another 1/8 L to the third power. So together that is actually 1/8 plus 1/8, therefore that's 1/4. 1/4 multiplied by 1/3, that's going to be 1/12. Here we have 1 L, here we have L to the third power. So together this becomes rho times t times L times, so 1/12 times rho times t times L to the fourth power. Now don't forget, we know the thin plate has a mass of m, and m equals to, again, rho times v, and in this case this equals to rho times t times a, the area. The total area is L squared. That's the area of this square. Therefore, if m equals to rho t L squared and Iy equals to 1/12 rho t L to the fourth power, therefore, we can substitute m equals to rho t L squared into this equation that we just derived. Iy in this case equals to 1/12 m L to the second power. So that is the answer to this problem. And now we have derived this formula. Later on, when we encounter problems involving uniform thin square plate, and we need to calculate its mass moment of inertia about this vertical axis passing through its center of gravity, we can use this equation directly.